And without any further delay, I will allow the speakers to take the stage and start the session. So have a great session.
Hello, everyone. Thank you, Rui, for the introduction. Let's start. Let me start sharing. Okay, the screen. Sorry, 1 minute. I'm just sending here some permissions of the system to be able to share.
Okay, let me just check.
Sorry, guys, I need to reconnect to the to the call. I really understand.
I can make you a co-host. Maybe you'll be able to.
No, it's just a system
okay.
requisite.
Okay.
Okay, sorry for this little incident. As I was saying, I'll start sharing the presentation. Okay. So are you seeing the presentation, right? The slides?
Yeah.
Okay, so thank you. Welcome to our workshop. We're going to talk about a little bit of how to build an exploration environment ready for production. Okay, my name is Carlos Alves. I'm a machine learning engineer, as we said. Basically, I'm working nowadays. I'm working in Basecone, and my job is to work closer with data scientists to bring what the outputs of their work, which are the models, the model artifacts, and deploy them into production to give to the clients of our companies the AI capabilities in our systems. So I'm responsible to build the infrastructure, build all the applications needed, and give support to the model development to data scientists and bring this to deploy. Okay, I've worked as machine learning engineer also in Farfetch and Talkdesk, and now I'm currently working in Basecone.
So my name is Tomás. As we said, I currently work in Basecone. My main task is doing research to custom products that we deliver. And of course, as my bio said, I'm also in a PhD program with focus on natural language processing, and that's it. So moving forward, in our workshop, in the theoretical part, first you are going to do a small introduction about how to do, what are the constraints in deployment models and common issues. Then we'll show a little diagram and explain a little bit how the models are developed and researched normally, and what is the workflow for production. Then we are going to talk about the focus of this workshop, so our solution architecture, and also a little bit how to deploy the models and how to store them. After that, we have like a Q&A for questions that you have, and then we pass it to the workshop. So when doing research and deploying models, sometimes appear some issues. such as the code quality science in research. Sometimes the approach is doing POCs, so proofs of concept. So normally, or sometimes the data scientists leave the code and the explicitity of the code and the code quality a bit left on the side, and just want to see if they can get some results. However, when they get some good model, the idea is the machine learning engineers pick that up and try to reproduce for a production environment. One of the issues is that it creates duplicated code, because you have one side the POC and another for production, and sometimes passing this information from data scientists to machine learning engineers could be a bit difficult sometimes. Also, sometimes different languages are used for research and for production. This could also affect, because other side effect is the different dependencies, because the POC can use some dependencies, and then when it goes to production, it uses others, and could cause some model drift. The data quality also could be an issue, because the data that is used to train the model could be different from the production, and we try to mitigate that also in some way. And when we are trying to solve a task and deliver a product, exist multiple solutions for that, and different models have different needs despite solving the same issue. And if we solve this in a POC and then move it to an MVP product, sometimes could be hard, because you have to reproduce everything, and the iteration cycles for the deployments go huge. So our proposal is to try to organize the structure of the repositories for the research and the deployment a bit different, and that way try to mitigate these issues, or some of them. So when we are developing models, so doing research, generally have a data set that we have the annotations and the sample, and all the data is already cured. And then we have the data loaders that pick the sample, and we have data pipelines that the data pipelines will pre-process the samples so it can be given to the model. And in the training, sometimes we also use data augmentation to try to virtually augment the number of data. Why? Because annotated data is pretty expensive, and this way you can get in an expensive way more data to make our models more robust. On the optimization part, the model is given the samples, it produces an inference, then it produces an output. The output is compared with our annotation from the data set, and we have a cost function. And then we have an optimization. So we produce the backpropagation, and we update the weights, and so on. During this process, we are going to log the metrics around loss functions and other metrics that we might need. We also, along after the training, during the iteration cycles, we also save the model using checkpoints, and since the cost function and the output of the model is not always the same as what we really want as an output to our client, we need to add some post-processing, and it can vary the accuracy and the F1 score and so on the post-processing. So we also have some post-processing that we use during training, but it's just for metrics and checking some parts. For the model deployment or the production workflow, it's a bit different. So we have a request from a client, but we don't have a data set and an annotation. And then we also have the pre-processing steps. However, we do not want to do a data augmentation. We want to use the raw sample. For the model, when the data is pre-processed, we do not want to since we don't have the annotation, we cannot calculate like a cost function. So the model just produces an output, and that output is just used for post-processing. So it can be given to to the client, but we log metrics, but not the same metrics that are logged during the training of the model. Neither do we save the checkpoints from the model because it's not training; it's a static model. Moving on. So our solution is to have two repositories, mainly one for training and research and another for the API. The training repository, what we do is we separate into different models. One that is for inference, that contains all the information around the overlapping between the training part and the production part. So the model architecture, the pre-processing transformations, the post-processing transformations, and the processor. The processor basically is something like a compose, will sequentially apply its transformation to the sample, to the input. And in these pre-processing and post-processings, we build these transformations in small units that only do one and only one thing, so it can be easier to do unit tests and to also build some modularity on the data pipelines, pre-processing and post-processing. Then we have another training model inside the same repository that has all the things that are needed for the training part. So all the things that's related with the data set, the data loaders, the transformations for the data augmentation, the custom loss functions if needed, the training code to do the optimization, the propagation, and so on. The callbacks for the checkpoints and how to do the checkpoint storage, the metrics, and that kind of things. When you're training the model, basically we save that checkpoints in a registry where will stay the model artifacts. And now Carlos will explain how is the serving layer.
Yeah. So in the serving layer, if we normally the models are deployed inside the REST API. So we're going to have these two repositories, the one that Tomás explained for the training, and we will have the other one for the service that will actually serve the model. So, and in this application, we're going to need to pre-process the requests, the model. We're going to perform a model inference, and we're going to do a post-processing. So what we're going to propose is that the inference model will be an independent package that will be exported and installed as a dependency of this new service. And in this way, we guarantee that we are using the same code in the pre-processing and the post-processing part that was used in the training of the model. So also in the model inference, we're going to import the model artifacts that were generated in the training model. That will be important for the and useful, right, for the model inference. In this way, we guarantee that we don't have duplicated code. All the code that is in the training repository, all the transformations of the pre-processing, the post-processing were already tested. So we have test coverage in all these transformers that we are going to use in the production side. Also, this code was reviewed by the data scientists and the data engine and the machine learning engineers. So we have a certain assurance that this code has the quality enough to be used in production. And that's it. With this approach, we make sure that every transformations that were used in the training part are test coverage, because we have unit tests for each transformation, and we have some modularity in our process, because since these transformations are independent, we can build pipelines of transformations, easily change the pipeline of the transformations, add one, remove others accordingly to what has been done in the training model. It is packageable because we are installing these transformations as an external package in our serving layer. So it will become a dependency of this service. We have reproducibility in our pipelines, because for the same request that is processed, for a request that is processed with the same pipeline of transformations, we have we are sure that in the end we're going to have the same results. And by all these reasons, this is a robustness approach, because yeah, everything was tested. We got the pair programming and the code review of both roles, and we are sure that this code has quality enough to be deployed in production, the one that was used in the training of the model. This approach also brings some team workflow benefits, because in this way it's easier to plan our work, since this approach is so modularity, is independent, the transformations are independent, so it's easy to plan the work that we need to do to deploy a new model, to build a new model. Also, as I said, there's a close work between the data scientists and the machine learning. They work together in the reviews, in pair programming if needed, to guarantee that the code that is produced has quality enough to be deployed in production. The cycles of iteration are smaller, and we can deliver products faster, because we don't have repeated code. We don't need to rewrite the code that was used in the training, because they're already has been reviewed and they have quality enough. The language used for the training and for the production with this approach are the same, because we are using the code. We are using code used in the training for the production, and we have improved quality and readability of the code by all these aspects that I mentioned. Talking a little bit more about the model deployment, when are talking about this, about deploying a model, there are two most common approaches for this step. One is to download the model artifacts when the server is starting up, and the other one is create a layer inside the application container with the model artifacts inside it. In the download model approach, we can see here that we have the repository which has the API service code with the repository. Certainly, it will be converted. We're going to build a Docker image of it, and we have installed the Inference model package as a dependency, as we said. This Docker image will be deployed in a serving cluster. It can be a Kubernetes, for example. And when a server is starting up, it will download the model artifacts from another third-party infrastructure. It can be a model registry, it can be a S3 bucket. But the thing is, we have this external dependency in this step of the process. One thing that can happen with this approach is that, imagine that the third-party application is down. So we're going to have a problem with this approach, because the application will not be able to download the necessary files to perform the inferences, and our application will not be ready to serve traffic until it downloads all its dependencies that it needs. So here we have this dependency, an external dependency of infrastructure. But this approach also has some positive aspects, because the Docker images are smaller, because we don't have the model artifact inside it, and also it can be easier to download to deploy multiple versions of the model, because we only need a generic Docker image of the application, and and we can control the model that will be deployed through environmental variables that are set in the deploy of the application. And this way we can serve with the same image, deploy multiple versions of the model. The other approach is when we store the model artifacts inside the Docker image of the application. Here we can see that to build the Docker image, we're gonna use the code, the API service code. We're gonna create a layer with the model artifacts and install the inference package model used for the pre-processing and post-processing and of the application. And then we're gonna deploy this image in the serving cluster to serve to make the inferences of for the request it receives. So in this step, with this approach, we don't have this external dependency. This is a simplest solution, a more simple solution for model deployment. We can store these artifacts inside the repository if they are not too large. Otherwise, we can store them in the model registry or another store service that it fits your needs. And yeah, basically the theoretical part it reaches hand. I don't know if you have some questions about this or not before moving on to the hands-on part, the workshop part. No,
I don't think so. Yeah.
Okay, thank you. So passing to the workshop. Tomás.
Yes. So now I'm going to do a little introduction to our workshop. So we are going to imagine that we belong to a news journal, and what our manager wants is to verify that each article is tagged correctly, and they could be world, sports, business, or science and technology. But fortunately, already exists a dataset for this. That is the one that we're going to use. That is AG News Corpus. It contains around 120,000 samples for the training part and 7,600 testing samples. For our model, we are going to use a simple neural network, but we are not the workshop is not focused on this part, so it doesn't really matter. The model that we're going to use is word-based. Yeah, I can pass it. Sorry.
Okay.
So a quick intro to natural language processing. Our model is word-based. What does it mean? It means that it's what is given to the model is split by words. So the data set is composed by an article that is a string. So the input is a piece of text. And the first part that we need to do is to tokenize it. So what we want to do is split it by tokens, and these tokens will kind of represent the words that they have. So in this case, we have this is a random workshop that is splitted, as you can see in the second part. And then we have to move it to something that the model can really receive as an input. So what we do is we build a vocabulary, and that vocabulary will give an integer for each word. So in this case, this is going to be represented by 1, E is by 2, A by 3, and so on. This will be like a list of integers, and then we have to convert that to an input tensor. That is something like a NumPy array or something like that. That can be given to the model, and the model receives that input and will do its inference and will result in a prediction. In our case, the prediction will be for output, so it will be the science and technology, the business, the world, and some other and sports, exactly. What are you going to use in this workshop? So for the training part, we are going to use PyTorch and NLPiper. NLPiper is a library that me, Carlos, and Daniel have built. that integrates multiple tools of NL for natural language processing and tries to simplify the pre-processing part. We are also going to use for training PyTorch Lightning, that is like a wrapper, something like Keras for TensorFlow, that eases your burden around the training part, the logging and that stuff. Talking about logging and tracking the training part, we are going to use MLflow. For data quality, we generally use the Pydantic, and for deployment, we are going to use REST API, Fast API. During the development, we generally use MyPy for type checking. We use Flykate for PEP8 checking to see if all the rules are complied. PyTest to do the coverage testing and unit tests, and PyDocStyle to see if all the doc strings are correct. And now I'm going to share can I pass it to the next slide, yes, please, Carlos? So here we have the resource that we need. We're gonna
pass them in the chat, maybe. Gonna copy paste that to the chat if you want to.
Yeah, if you
to follow.
That, please.
Oh, sorry.
Carlos.
Okay, I'll stop share. And I'll copy the links and paste them in the here in the chat.
So hopefully I'm sharing the right window. Could you share the Google Colab, Carlos?
Yes, I'm writing it right now.
Okay. So if you could please open them, we will wait a minute or two. So about the workshop, as we said, we are going to train a model to try to classify the news. Here you can see the project structure. So basically what we're going to do in this Google Colab is we're going to clone another repository that we have already built that has all these steps. And we are going to build one thing or two just to show you why we did in this way. And to have like a bit of taste in this part. Then we're going to move to the parts around the deployment of the model. So as the structure of the project, as you can see, you have this part that is like contains all the information about the inference. So we have the model's architecture, the data processors that's going to be used for the pre-processing part. In this part, we only have like the vocab transform implemented. Here we have everything related to the training part, so the data sets and other parts that you need to train. We here have the script. Generally, we do not use notebooks to do explorations or to train models. What you do is we launch a job in a server. We use AWS, so generally we use an EC2 instance or a SageMaker job to train our models. Here we have just some unit tests. We are not like in this repo, they are not like heavily tested due to time constraints to do this workshop. So the first part I have to do is press here. So this is just to set up, so to do the git clone, to enter in the repository that we have built, check if everything is already up to date, install the dependencies, just another part. Generally, what we use for to deal with the dependencies and that kind of things, we generally use Poetry. And Poetry is really useful to us to let me see if I can open to try to solve all the dependencies. So for example, here, just to show you, we here have the package. So this is what is going to be added when we train when we do a pip install using, for example, Git. That is possible. This says, okay, that you can use Python 3.7 to upper. Here we set some dependencies that could be optional. So for example, we do not need for production MLflow, Torch.data, this NLPLG that is for data augmentation and TQDM or PyTorch Lightning. So we add this as an extra. Here have also our dev dependencies that when we install the package for like a production environment, this is also not installed. So basically, in this case, the only part that is installed is the NLPiper and the PyTorch. That is already a dependency on NLPiper in TorchText. So moving on, so probably you already did the pip install. Some colleagues of mine said that due to some dependencies that got wrong, if they press again, which will save some time when you're going to pass to this part. So I'll just press it again. Okay, everything is right. Here is just to do some basic imports from the libraries that I'm going to use and what we already have. Here we set just some hyperparameters to set our training. So the number of classes that we want to train, the number of epochs, we are going to set to 2 to be faster. So the first task. So the first task is to build the tokenizer. What you're going to receive is basically what you have is we have the base transformer. The base transformer is like a class that is going to be inherited for all the other objects that are going to do like preprocessing stuff. And what is needed to be done is it's given an input that is a text, that's a string, and the output must be a list of strings. So given a string, the output that must be delivered is this one. So I will wait a minute or two to do this part. So far, do you have any question or something similar?
I don't think so.
Okay. So what we need to do for this part, we need to do text.split, and basically we add a space because we want to separate by the spaces. This is the most basic tokenizer that exists, but for this case, it's more than enough. So we are going to initiate this class, okay? Okay. And now we are going to build the vocabulary using our processor. So basically here we have the vocab, that is what is going to give to each token an integer. And here is our transformation that we just got. So basically what happens here is we build this processor. The processor, when is given the transform, that is going to split the text by tokens, it's then given to the vocab, and the vocab change that to a tensor. And in this part, we're just going to build the vocabulary. So if we run this part, we'll build the vocabulary. And of course, it's, yeah, okay. Sorry. And now it's being built. Sorry. So as we can see, our vocabulary is around, now it's around 200,000 tokens, and we are going to try to modify it to remove the punctuation. So we can try to make this smaller, the vocabulary to be smaller, since our model is going to be also smaller. So here are some tips and tricks to use this from strings, the punctuation. This basically has all the punctuations that we want to filter, and the make trans is to build to map one word to another word, what we want to change it, and this is to translate one part to another part. And here you also have, if you want to try to implement this, you also have like a references here to try to implement this. So I'm going to wait a little bit so you can try to implement this part. You should do this this transformation here. So since you want to remove the punctuation, you can do previously to the split, and you can do in text. So for example, text equals to something. Let's apply on text. I think it's not it not past 5 minutes, but since I have no clue if you already did it or not, I will continue. So basically what you need to do is this is a bit tricky, so I have to do a translate and then do a string make trans. So I put it there and just open and put here duration. And now when you're running this, we can run this part and the vocabulary will be smaller. So we previously had 188,000. Now we have a little bit less. Another thing that we can also easily do is just to lowercase everything. So I can just go here, say lower, and we'll lower the strings. And if you do this, basically, we can lower the number of the vocabulary. However, we enter in the part that I said previously that we want the transforms to do one and only one thing. And that's the idea, that you can do that them sequentially, and what sometimes happens, and what I have seen in my life as a data scientist, that sometimes we do a transform that does a lot of things and no one has a clue what does it does and why we have to run them like that, and when we change something it goes completely wrong. So we can divide this, for example, in a class that just lowers the case. So we can just do it like this, base transformer, and we can implement the class call. You can let as it is, but I'm just like showing that how to do this well. So we are just adding typing. So here we are just going to return the string, and to return we just need to text.lower. So here we have the lowercase scenario. Now we can also implement the remove punctuation. That basically is going to be this. So we have also the remove punctuation, and now we can have here the tokenizer, and the tokenizer does this. Yeah, so basically this is it. And now instead of having this, I can just have the first part. I want to lower the case. Here I can just remove the punctuation, and here I'm going to tokenize it. So hopefully everything is going to work exactly the same. The easier part to work like this is we can like play around adding or removing stuff to see what helps and what not during the training. And when we try to move it to the production side, it's also easy to implement it because everything is already implemented. The idea also is to have everything that enters here tested to see if everything corresponds to our expectations. So moving on, and now I'm just setting up the data. This has to be with like data loaders and things like that. Here we are just setting up the environment for training. We are not focusing on this part because each person does in his way. The main part is just doing separate the inference from the training part. And here we are going to train the model. So the model should take around, I think, 2 minutes to train, to do the 2 epochs. So the model is trained. You can see it here also that it's already on MLflow. In our company, what we don't save it like locally. What we have is like a server, and that is connected to RDS, so a database, and also to an S3, that's like a storage thing from AWS, and all the logs and metrics goes to the RDS, that we also have like a UI that I have here open for these experiments, and then all the checkpoints are saved on the S3. So now we are just going to implement the data augmentation for training. What we want to do is we want to use synonymous augmentation. So basically what does this do is this change some words for some synonymous a bit randomly. And we have here some ideas how to do it. So here we also have this is a pre-processing task. This is it's wrong here, sorry. It's supposed to return a string. So the sequence augmentation inherits from base transformer, and here has a data augmentation. Why? Data augmentation is, we set it's always to false. And when we have a sentence augmentation, we set it to true. And then what it does is the processor sees if it's like supposed to apply data augmentation or not, depending if it's training, if it's testing, if it's validation, or if it's in production or not, and then it applies it or not. Afterwards, you can see that in the repository when you have time. So now we have about, I don't know, 5 minutes. I don't think that's really necessary because it's just look into it in this part and implement it here, and it's basically already implemented. So I'll wait a little bit. I'll just do tokenizer because we changed it. So I know that it's not past 5 minutes, but doing these kind of workshops offline is a bit strange. So I'll just start implementing it. So what do we need? We need to download these parts that are mandatory. I'll just put them there to be easier. So when the object is initiated, they will download this thing. Here I will also initiate this object, and then I will use here this object. So it's just return self.aug note and text, and so it's implemented. This is supposed to be like in another part. So this is supposed to become to be stored in data augmentation, and then we have here the same implementation that is here. Then we also would build the vocabulary. Despite it will not change the vocabulary. Now it's going to appear a bit higher because you're only applying tokenizer, but it's the same thing. So adding or removing doesn't matter because we are applying we are not applying with data augmentation. So in the processor, we are saying, okay, do not apply data augmentation if it appears. We'll skip it. Then you should train this part but since the resources in Google Colab are a bit scarce, you only have like 2 cores, so I'll just pass on. And here we have the NL Piper that I told you about. This just a bit to sell our package, nothing more. So what we did here is also have like make that our processor has like an integration with this repository, and then this repository already like have a lot of transformers that are applied that can be used for natural language processing, that already has a lot of checks, and then you can just like clean the punctuation, do some basic tokenization, and also lower the case of the tokens, and we'll remove everything. It's similar to the previous part. The advantage is that instead of having to implement everything by yourself, it's already implemented, and we just like do a wrap around it. I will not train it because we'll give something similar to the results previously that we got. I'm just waiting to finish building this vocabulary. It takes a little bit more time because in here we are using Pydantic, and Pydantic is checking a lot of things to see if like the data that is received is really strings, if this, and when we tokenize that the tokens are correctly splitted, and we have a lot of checks, and that the sequence that we are applying is correct. You cannot like are some process that you cannot do. So for example, if you pre-process, if you remove the punctuation from a text and then do a tokenization, you cannot apply again like something on top of the text, because it does not make sense. It's only on top of the tokens because I already tokenized it. And we also save it all the data. So we have always the original sample, the cleaned up sample. When you tokenize, you have a list with the tokens, with the original tokens that was gotten by the tokenizer, and so on. If you want to apply it like lemmatization, you also extract lemmatization. So, and as I said, this the Google Colab, we are only using the CPUs, and only has like 2 processors, so 2 cores. So. And that's it. So basically now we are just zipping the files, and we can use them in the next part. So, and we track everything using MLflow, where here we have the model training only using the tokenizer. I don't remember if I added the clean punctuation or not, but you can check it. With NL Piper that has it, and using the sentence augmentation, then we can just see how they perform it and compare them. You can see what was like during testing, what was like the front score. Segment augmentation did not help in this case, and you can just use it and abuse it of the MLflow to see what happens with the model. So now I'm going to pass to Carlos to continue. So here we build it the zip file that already contains the model that you trained, and now you want to put it in production. And so how do we do?
Thank you, Tomás. I will share again my screen to go to the second part of the workshop. So going to the training part. Okay, so for the for the serving part of the model, we're gonna, in this workshop, we're gonna build a custom API to serve this model that we have previously built, and this is the architecture that we're gonna follow, which is to create an API that will have the inference package as a dependency and also the model artifacts. The model deployment approach that we decided to use for this workshop, for the sake of simplicity, was to store the model artifacts together with the service code. So everything will be together. We are not going to store these artifacts in the third-party application. So it will be closer to the code of the application, the model artifacts. So what I'm going to ask you is to clone this repository, the NLP API, which will contain the code that we're going to use to build our API to serve the model here locally. You have here the repository. I already passed the link to the repository. You can clone that. As the same for the dependency, to install the dependencies and create a virtual environment for this repository, we're going to use Poetry. Personally, I locally use Poetry, but you can use whatever your tool you are more comfortable with. I also have uploaded the requirements file, so for you to be able to build your virtual environments with other tools. And while you do that, explain a little bit about the project structure. So here we're going to have a folder which we'll call MEL, which will have the assets of the model. In this case, the model weights and the vocabulary needed. And here we have the pipe project TOML, which is to build the virtual environments with Poetry. The setup config file it stores the configuration of those auxiliary tools that Tomás already mentioned. And in the source folder will contain the main logic of our application. We have a logger file to configure a logger of for our application in a JSON format. The main.py file will contain the REST API code, and we have a utils file which will contain some functions that we'll use for the inference, and also a file with the version of the API. And here in the tests we have some basic unit tests for the endpoints. So to start to build the REST API, the core library that you're going to use, it will be Fast API framework. This lightweight framework will enable us to easily create and develop a REST API using UVcorn as a server which lets us to do async programming with Python, and it uses Pydantic to validate the requests and also the responses that of our API. So as I said, for this tutorial, the code will be incrementally written in this in the main file. And how do we instantiate a Fast API object? So the main code here is we only need to instantiate this Fast API, import and instantiate this Fast API object. This will create. This will be the hub object that will instantiate the application when we run the program, and it will start handling the requests for the different URIs defined here. And now we can define a simple endpoint. We just need to create a function, have an annotation saying indicating that if this endpoint will receive get requests, post requests, and what is the endpoint. We can also define here in the notation what is the status code that we want to return, and what we're going to return for that endpoint. In this case, when you start the application, what we're going to see if you make a request to this root endpoint, what you're going to see is what's the version of the API that we built and which environment it is. So we also have a makefile with some commands that facilitate some tasks that you're going to do. One of them is to start the API. You can only do by typing make API and running these commands. what will be executed with this command is we're going to start the UVcorn application, the UVcorn server that will start serving requests traffic for our fast API application. So let's start this. I already have cloned the repository, and if I run make API, it will start running locally. And you have here the link to the API, and if we open, you can see that it will return us the version and the environment that we are. And back to the application. One awesome feature of Fast API is that it automatically generates documentation of our application for us, of our API for us. So if you go to the endpoint docs, you can see the documentation of our API. You can see all the endpoints that we have defined here, and this Swagger UI enables you to interact with the application, with the endpoints, without any other external tools. You can use what you prefer. You can make calls directly to the API through curl or using the Postman tool. But you can, by using this Swagger UI of the documentation, you can also interact with applications. So, for example, to the root endpoint, you can try it out here and send a request, and we're gonna see here the response and the status code that it returns. And you can see here that we already have defined an inference endpoint. So if you look to the code that are in the main source file, explain you a little bit what we have here. Here you can see that we are defining our fast API object that will start our server, our API. And we have here defined the root endpoint that I've shown you. And also we have two other endpoints. One is the health endpoint, and the other one is the ready endpoint. And they return, the default return of them is 204. So these two endpoints are defined here because normally they are used in the Kubernetes cluster. The health one is used to check if the application is up and running. And the ready endpoint is used by the Kubernetes cluster to check if the application can receive requests, can receive traffic to serve the requests, okay? So this is just for you to, an indication if you want to deploy this application later in the Kubernetes cluster, probably you're gonna need these two endpoints, and they are already here defined. So the other one that it's important to us is the one that will make the inference of the request when you send a text, in this case, a news to the application. You want the API to classify that news and say which class it belongs, okay? So if we make a request to this endpoint, let's see what happens. We're gonna send the text string. It can be something. We're just gonna need just an example, and we're gonna execute. This is it. This is the request body of the request. And if you execute, we see here that we got an error code saying that the endpoint is not implemented, and the details says the inference endpoint is not implemented. So this is going to be our exercise for this workshop, which is to implement this endpoint, inference endpoint, for us to be able to, for a given request, make an inference and return which the classification of the news of that request. So one thing that I forgot to mention is that we can, as I said, we're going to use Pydantic to validate the inputs and the outputs of our application. And now we're gonna, and how we do that. You can see here we have two classes here. One is called news, and the other one is news classification. And as you see here, we say that the class news only has one field, which is text, and it must be a string. And the class new classification has two fields. One is a classification with a type string, and the other one is a confidence with a type float. So as you as you understand, the first one will be the data model for our requests, and the other one will gonna be the response of our application. Okay, so here in if we check here the utils file, as I told you, we have here some utilitarian functions for the inference part. We got here a function to load the model. As you see here, as I told you, we're going to install the inference package as a dependency of this application, of this API, and this is where we import that package. And we're going to use the baseline model, which contains the model architecture, and then we will load the model from the checkpoint, which is already here, the assets. One of the assets, it's this model pickle, which contain the model weights. So we're gonna create this model object and load it from the checkpoint. We also have this get processor function and the get post processor function. So our first exercise will do to implement this the logic for the inference endpoint, and to do that I'll already give you here the code to make the inference. And what we're gonna need is to implement the pre-process pipeline and the post-process pipeline for these endpoints for us to be able to make inferences. If you notice here, the first thing that we do after the application is created is to load the pre-processing pipeline, load the model, and load the pre-processing pipeline. This is here because we only want to do this one time, and this is saved in memory. And if you move this code to the logic, to the function of the endpoint, well, it's not so performatic. It's not so performatic because in that way, this is going to be loaded every time you receive a request, and there's no need to do that. We don't need to load one time and use these objects for every request that the application receives. So I will give you a little time to implement first here the pre-processing pipeline, and after the post-processing pipeline. This is very similar. This must be the same pipelines. Remember, must be the same pipelines that we use to train the model. So you can recap what you've done in the training part with Tomás, and implement the same pre-process pipeline using for you. Maybe it's easier for you to use the Daniel Piper library, which already has the transformations needed implemented. So I'll give you a few minutes, and then we implement together this logic of the inference endpoints. If you have some doubts, raise your hand and ask. So I think we can start developing this together. So let's start by defining here the pre-processing pipeline. As you can see here now, the pipeline is empty, an empty list, but that's not what we want. We must be sure that we must be careful, because the preprocessing pipeline must be exactly the same that the one used in the training part. So if you remember, in the training part, you remove the punctuation, you had a tokenizer to split the words, and also you have lowercase them, right? So that's, and also you have the vocabulary transformation, if you remember. So that's the pipeline that we need to implement again. So, and we're gonna use the NL Piper transformations. So we define here a pipeline. Sorry, it will be on a pipeline core. And here we're gonna need the compose. And in the inside the compose, we're gonna define our set of transformations, which gonna be the NL Piper transformers inside, and we have the cleaners. Inside the cleaners, we have the clean punctuation, and also we want to have a tokenizer. Inside the tokenizers, we have the basic tokenizer to split the words, and we're missing the normalizer, which is to lowercase our request, which is the class case tokens. So this are the three preprocessing transformations that we've done, and also we're gonna need to add the vocab transform. This is already a variable defined here with the vocab transform defined here, so we're gonna use it. And basically that's it. This is the preprocessing pipeline, and we're gonna return it, okay? And for the post-processing pipeline, what we're gonna need inside our inference package, we already have defined here a function of inside the post-processing transformers, and which does exactly the post-processing that we need. We only need to instantiate this class and pass it the class that the news can be, the tags, okay? So those are the preprocessing and the post-processing, and now we're gonna need to call them here in the endpoint part. So in here we can, for example, have a log of what we are receiving. For example, sorry. For example, this and this is okay. The requests object the requests that we're gonna receive is here in this object. Okay, this news argument will be the request that the application will receive. And if we do news.text, we're gonna have the text of the body of the request. Okay, so and for the pre-processing pipeline, we have already here loaded the pipeline. Do you remember? So we're gonna need to pass to the pipeline the text of the request that we received, which is done here. So we can also encapsulate this in a try mechanism. For example, we can log the error, and we can erase HTTP exception. Returning a 500 error and saying that we got an error in the pre-processing of our requests. Okay, so this raising this object will make the API to return the status code that we've defined here with this message. Okay, so and also we are missing here to print the error. Okay, so we are calling this our pre-processing pipeline with the request that we received here. And for the model inference, what we are doing here is with this with clause, we are saying that we don't need the gradient. This is used only for the training of the model. So this will make the inference more performatic, more faster. And we're going to use the model that we have loaded here previously, and we're going to pass the requests pre-processed and the model offsets for the inference. And after that, we will need to do the inference. Here you have the post-processing pipeline imported. So what we're going to need in the pre-processing part is to the news classification and the confidence will be equal of the post-processor with the inference inside. So basically, we're going to pass the inference of the model to this post-processing pipeline for it to return us the tag, which was predicted by the model, and its confidence. Okay, and this will be our just log the error, and if we get an error, we're gonna return this error coding. But here is saying that this is the post-processing part. Okay. Now we will not raise anymore this exception. Instead we will return an object which will contain the classification and the confidence. The important part here is that we are saying here that the response data model of this endpoint must be a new classification. So the Fast API framework will try to convert and assert if the object that we are returning is compliant with this data model that we have defined here. Okay, it has the field classification and the confidence, and here we have the same fields. So if we save here and also save, if we try to run now our application, the the Fast API is the way that we launched our API. It has a reload mechanism. So each time you do changes in your code, the application reloads. So now if you go here again and try to make a new inference to the endpoint, but now instead of saying a string, like if we say, like, for example, I like to play tennis, and if we send this request, okay, the model infers that if this was a real news, the model would say that it is sports related with a 99% of confidence. Okay, you can try another one. Now let's try to aim for the business part. For example, the world economy, I don't know, is growing. Okay, business. And you can now play around with the model, try different approaches, try different sentences, see what's the model output. You can try to train new models and try to improve it. And basically, this is what we bring to you. The next step will be, this is, as you understand, running locally. Next steps will be try to deploy this in a cluster, in a Kubernetes cluster, and try to make it available to the public and make it public. So this is what we got. This is what we got to you. We show you how we can structure the training repository to have these two models, and the inference model was installed in our serving application. You can see here in the TOML file that as a dependency, we got our NLP training, which you will install the package directly from the GitHub. And by doing this, we just need to be careful to define the same pre-processing pipelines and the post-processing pipelines. And basically that's it. This is a way we arrange to do not have duplicated code, to have faster iterations of development, have independent transformations tested and implemented, and this way have a closer work between data scientists and the data engineers. And I hope you'll like it. I don't know if you have some questions for us. Oh, just to mention, this repository also has, if you want to do it also has a Docker file if you want to, and in the make file you have some commands to build the Docker and to run it through the Docker. If you just to want to play around with this and explore a little bit, you can also have this available for you to build build a Docker file of this application, and that's it.
All right. I don't think there are any questions. Last chance. I don't think so. So thank you, Tomás and Carlos, for this valuable session.
Thank you so much.
We are sure that it will be very helpful for the participants to face the challenges and hopefully for their careers as well. Thank you to everyone that participated in the session. I hope it helps you to come up with great solutions. On a last note, I would like to remind you that in the next few days, the recorded workshop and the session materials will be made available in a Discord of World Data League. Carlos and Tomás, is there anything else you would like to say before we close the session?
Just to thank you to the organization and every participant. If you have any question, you can reach us in LinkedIn and we can have a little chat.
Thank you.
Okay, so that's all for today. Thank you for coming, and we'll see each other in the next session. So goodbye.
Thank you. Bye-bye.
Thank you so much.